Hello, my name is Maciej Krosta, and today I would like to talk about multithreading in vision inspections. How to use, how to create a multi-threaded application, what are the risks associated with it, and what to know about it. So let's start with explaining what is a multi-threaded application. It is an application that utilizes more than one thread to execute its computations. There are many reasons why one would want a multi-thread application, but the most common probably is the increased performance it may entail. Imagine a complex vision task that has a lot of parts that could be done in parallel, but have to be done in sequence now because we have only one thread. If we modify the application to utilize multiple threads, we can split the complex task into smaller subtasks, which will be executed in parallel, which may provide substantial increase in performance. However, some would also want to use multi-thread applications to increase the efficiency of the system. And by that I mean, if we have multiple production lines, for example, and we need a computer that will oversee them, that task may not be really difficult computational-wise, so there is no need to have a dedicated computer for each line. However, if we want to use one computer for multiple lines, then we can only check the production line one after another in sequence. We cannot do it in parallel with only one thread. But if we were to use a multi-threaded application, then each of the line can get their own dedicated thread, and it will be overseen in real time in parallel. So instead of having 4 computers for 4 production lines, we can have only one with basically no decrease in performance. So it will be much better when it will be much more cost efficient. The other reason to use multi-threading applications is the ability to separate tasks based on their goal. For example, we may have an application that on one hand establishes communication with another device and communicates with it. On the other hand, inspects items on the production line. We probably don't want a situation when a failure in the communication thread in the communication task would cause the inspection task to also stop being executed. And the inverse is also true. If there is an error on the production line, we don't want the communication to stop. So we can give those tasks their own separate threads that will be largely independent from each other, but we will still be able to exchange data between those 2 threads. Currently, most of the vision frameworks on the market are largely sequential in nature. There is very little parallelization. Some frameworks have some functions or filters that feature some innate multi-threading, but the user doesn't really have control over it. If a framework somehow allows the user to implement their own explicit multi-threading, the threshold of entry might be quite high, especially for the inexperienced user. But you may ask, what are the risks of multi-threading? If some data is accessed by multiple threads at the same time, there may be some undefined behavior. For example, if thread A reads a list of results, but thread B at the same time removes elements from the list, then thread A gets false data that is not true for the current iteration, nor for the next iteration. It's in interim. And that is something that needs to be avoided. To avoid it, we can lock data. Every time a thread wants to access it, it has to be locked first. And when it is locked, no other thread can establish its own lock. The other thread will have to wait until the first lock is released. But this, in turn, carries another risk of the so-called deadlocks. If thread A that does not release the lock, then thread B cannot read the variable. And that may lead to a situation where the whole application stops because the lock was not released properly. So this is very important to be wary of and to avoid. Related to that is the issue of synchronization, where we have several variables that we expect to be from the same iteration, but it may be possible for the other thread to access them and modify some of them, which is basically the same thing with the locking variable problem when we have data from different iterations at the same time. To avoid it, we can either lock multiple variables into one group them into one group and lock that group, or to put the variables into some larger structure and lock that structure or class. So let's go back to the reasons for multithreading, and let's review the first reason: increased performance. We have a simple application here, a production line of some drinks, beverages. The main orange thread acquires the image from the line, locates bottles in the image, and then sends the coordinate of each bottle in the image to 3 different threads that each detect label defects, check liquid levels, and read expiration date on the bottles. After that, after sending the data to those threads, the orange thread waits for the results as long as it takes for the slowest of the tasks to be finished. And after receiving all the results, it concludes the inspection. What is important to notice here is that those subtasks are fully dependent on the orange task, the orange thread. They cannot be run by themselves, and they will be only called when the orange thread needs them. And I have prepared an application that we will modify to feature multithreading. As of now, it is very simple and sequential application that inspects 2 sides of one object in some given time. As we can see, the iteration time for the inspection is about 900 milliseconds. And this is with the inspections done in sequence. Let's review the application also, a bit closer. Loading the images from the hard drive, inspecting each of the images, displaying the results onto the HMI, displaying the measured time. I need to inform you about the fact that the inspection has been artificially slowed down with the delay filter to better show the effects of a multi-threading approach to this application. So remember that as of now, it takes about 900 milliseconds to finish the iteration. So how to make a multi-threaded application? First of all, we need to add another thread because we currently have only one main thread. To add a thread, we need to add a worker task, which in Adaptive Vision can be used as a parallel thread. Let's call it side A. However, if we were to run it now, side A would only be ever run once because there is no looping. So we need to add a loop filter, and now it can be used multiple times. Now we need a way to send data, the image, from main to side A. We can do it with queues. A queue, which can be created here, is basically a list where after reading an element, this element is removed. Let's call it side A image. It will be the type of image. The size of the queue matters when the speed of threads is different, or rather, when one thread can run multiple times when the other makes only one iteration, for example. In this case, both threads will be synchronized. Side A will not be able to run without the image from main, and main will not be able to finish its iteration without side A results. So you can limit the size of the queue to 1. So when we want to read data from the queue, we need to use queue pop filter with the queue name of side A image. And in main, we need to add the element to the queue with the filter queue push. Now we see that the A inspection is basically this filter with this input parameter. So we can cut it out and paste it here. Of course, we need to input the same parameter. So that would be the inspection. But we need to send the results. To send the results, we need to create another queue. Side A results. Now, the type of the queue will be type result, which we'll talk about soon. And the max size will be also limited to 1. Result is a custom structure, a user structure that contains an image, a Boolean value whether the result was OK or not, and an array of circles that mark the defects. Since it is in one structure, we are sure that the image, the Boolean, and the circle to the array will be from the same iteration. Because queues have, behind the scenes, a lock-in mechanism. So this takes care of the first problem and the last problem. With the multi-threading, the data will be synchronized, and we will avoid situation when data is from different iterations. To send the result, we need to use queue-push as before, this time with the other queue, and we send the results. Then in main, we need to add queue pop side A results, and that's it. However, if we were to run the program now, we will notice that not much has changed. The reason for that is, notice that queue-push and queue-pop are one after another, and then we conduct the B inspection. So here the program requests results from side A, then it waits for the results, and then it conducts the B inspection. And we can see it here, that queue-pop takes a long time because the program has to wait for the result. If there is no element in the queue, qpop will block the application. However, if we just move the qpop here and run the program, the time is much better, nearly twice as fast as before. Because now, during the waiting time that was previously idle, we conduct the B inspection. And we can see that qpop takes a very short time because we inspect the site B during this time. We could also create another thread for site B and have basically qpush and qpop for site B image and result. But that wouldn't really make any difference because after pushing the images, the main thread would have to wait. In fact, it may be even slower than now, because as you might notice, pushing also takes some time, because splitting the work into multiple threads has some overhead. So not in every situation we may want to use as many threads as we want. Let's go back to the PowerPoint presentation and go to another slide. So the example for increased efficiency. We have independent tasks. They are totally, they don't know about each other, basically. They don't communicate with each other. Cannot affect them one another in any way. So 3 production lines, acquire image from line, inspect image, send result. Very simple concept. Next, we have the more abstract one, when the tasks are divided into threads based on their goal. So the orange thread is the communication thread, and the blue one is the inspection thread. The orange thread maintains communication with some other device. If that device requests some inspection result, it may forward the request to the inspection thread. But if there is no request for an inspection, nothing is being done. Orange thread will also do some other things that will be not related to the blue thread. And if the blue thread, in the meantime, sends some result about inspection, it will forward the results to the device. And the blue thread will continue to run on its own. It may have some additional tasks to perform other than the requested inspection. And as we can see, the threads are not totally dependent on each other. They can run without one another. And we can exchange the data, but the data is not required for the iteration to finish. And the last example is the hybrid approach. With the hybrid approach, we can combine previously aforementioned paradigms to create an application that better suits our needs. So we can have a communication thread that will request inspections from either line A or line B. And those lines, as before, will do their own work, even if nothing may be requested, and will send the results back to the communication thread. So let's go to another example. I have prepared another application. We don't need to save it. In this application, we need to introduce another device, and this device will be simulated with a runtime program that connects through TCP and communicates with the program. So let's run this application, and let's run runtime. When we connect, we can see that we have 3 separate production lines that inspect some image for defects. They judge whether the object is correct or not, gather their own statistics, and if the object is incorrect, the application informs the first device. We can also, through the other device, stop the inspection and re-enable it. However, if we were to simulate a disconnection like that, and then we want to connect again, the program resumes. And what's more important, the statistics are also they are not reset. Even if we disconnect, this application switches to off mode, but it still preserves the statistics. So let's stop it for now, and let's look a bit closer into the application. In the main thread, we basically have the lob for TCP. The communication is established here and finished. And as soon as we can, we read whether the inspection is still active or inactive. The information about it is stored in a global parameter. We will then display the production status of the inspection on the HMI. And then we get to the send results variant macro filter, where we use qpop timeout on the results from the 3 threads. And this is important that this is timeout. qpop timeout, as opposed to the normal qpop, will not block the application if there is nothing in the queue. After the specified amount of time, which in this case is 0 milliseconds, if there is no value, a nil will be returned. And then in this step macro filter, we take the possibly nil values and format them to the string that we can see here, defects on line 1, 2, 3. When it comes to the threads, on the other hand, we can notice that they grab image here, 1, 2, and 3, as opposed to the previous example when the image was grabbed in main and then sent to the thread. So they start independently. They perform an inspection, calculate the statistics, and send to the HMI the results. And notice that each thread accesses the same HMI, but in different places. And it shows that the HMI is basically multi-threaded by default. There is no limit on how many threads can access the HMI. Of course, as with the queues, there is a locking mechanism. So if another thread wants to access the HMI when the other one is writing to it, the thread will have to wait. And after getting the results, it pushes the bool into queue. And we can, for example, disable a thread. Enable work in the backend is disabled now for line 3. When we run the program now, the first 2 threads are totally unaffected. The line 3 will not be run, its HMI portion section will not be updated, but the other 2 threads will work normally. Also, let's stop it again, or even not really. We can modify the delay value. For now, between every iteration for line 1, we wait for 200 milliseconds. We can increase it, for example, to 1000 milliseconds. And we see that it did not affect line 2, which shows that they are truly independent from each other. We can make it as fast as possible, or even slower, and the line 2 will not be affected. Also notice that those threads have an asterisk near it. It is a sign that the thread will require a special license. We can see it more in licensing, the tab, because those 3 threads utilize filters that are from Foundation Pro and Matching Pro, so it cannot be done with the standard license for one process and thread. But notice that main does not have the asterisk because it contains only communication filters and it basically performs no calculations. If we were to disable those threads totally, of course, there would be no result for the program now to share. But this program would then only need one license, normal license. It would not need license for additional threads. So let's enable it once again and run it for the last time. So let's disconnect, connect. And as we can see, the work has resumed. The production can be stopped. Even if we were to disconnect forcibly, the program will stop here, but it will not reset, and it will resume the inspection when the communication is established again. That concludes my presentation. Thank you for joining us in, and I'd like to wish you a good day.